In this video, what we want to do is talk about still columns and the basic features that go into designing a still column. And to begin with, I would like to quickly talk about section shape. This is a pretty easy topic for an introduction to still columns. When we're talking about section shape, still columns typically come in three basic shapes. So we'll identify these as the common shapes here. Think real quick, what would be the cross-sectional shape of a still column that you may have seen? Typical answers that I get from students when asked this question in class are circular. Usually they're hollow. We call those pipe piles. Also, sometimes they come in square columns, but they're also hollow, or we'd also say nearly square, and also wide flange shapes. Notice here that I'm drawing this more as an H as opposed to an I. There's no right or wrong way for this particular shape to be drawn. For some reason we tend to draw them as H shapes when we indicate columns and I's when we indicate beams. But the major difference when we're talking about wide flange shapes, or the W shapes, is that for beams they tend to be tall and fairly narrow in the flange area. Tall in the web, narrow in the flange. And with W shapes for columns, they tend to be square or nearly square. And you'll notice that each of these tend to be reasonably the same dimension in the X direction as they are in the Y direction, meaning each of the lateral depths of the cross section. And also note that they're typically hollow because we're trying to maximize the efficiency of the material that we're using. And the easiest way to do that and provide some shape stiffness is to push the material away from the neutral axis. So you'll see those two major features in all of these three shapes. Basically the same in the weak and the strong axis, the same dimension, and essentially pushing the material away from the neutral axis to maximize the material that's there. Occasionally you'll see built-up sections. Sometimes they'll design still columns that aren't something that you can go purchase over the counter. And so an example of this might be if you had a scroll up just a little bit. If you had a taller and reasonably narrow beam like this, notice it's tall in the strong axis compared to the width of the weak axis. So occasionally what they'll have you do is go ahead and weld a piece of steel plate on the top and the bottom, and essentially what you've done is now you've created a strong and weak axis that are nearly identical to each other. Another example might be where you have some sort of a channel shape, looks like a C, and might have one on the other side right here, and to create a column they might have you again weld a plate on the top and the bottom, and again we've created sort of a tube type shape now out of pieces that we've got. More often than not, if this built-up shapes were to be used on a project, they'd be fabricated in probably not on site, probably fabricated in a warehouse somewhere. The quick question to ask here is how would you calculate the moment of inertia and the radius of gyration for these two shapes right here? We'd go back to the composite shapes that we had talked about earlier in the semester, and you'd be able to do that. What about these upper shapes right here, the pipe, tube, and W shapes, the common shapes? Where would you get to moment of inertia and a radius of gyration for them. Those would be, because they're standard shapes, we'd pull those from an appendix. All right, let's switch gears real quick and talk about slenderness ratio now. If you'll recall, the slenderness ratio essentially was the length of the column divided by the width of the column. And with timber columns, we divided those into three basic categories. We had the long columns on the right, the short columns on the left, and we tend to design our timber columns in that middle section where we have inelastic buckling. With steel columns, we only use two major breakdowns, and we actually take and lump the first two together. So we'd have short and intermediate columns, and we'd have long columns. Now what we need to do is have a breaking point between those. The slenderness ratio on this end would be 0. If you recall, we talked about the slenderness ratio of 200 being the upper limit for steel. But we've got to have some sort of a way to define the difference between these two sections, because they're going to behave differently. And we do that with a parameter that we call C sub C. C sub C, if we pull from our textbook, is equal to this equation. 2 times pi squared times the modulus of elasticity divided by the yield stress of the column. And all of that is to the square root. And this would be the equation for C sub C. Because it has the yield stress in there, what you'll notice is that for 36 KSI steel, the C sub C equals 126.1. So just a little more than halfway as you're going through there, about 5/8 of the way there, really. For high strength steel, or 50 KSI steel, when you plug that into the equation, C sub C equals about 107. And note that there are no units on this. These are a dimensionless number right here. But those are the breaking point values for where we determine where our short and intermediate columns end, and we switch over to our long columns. Why would we care about this C sub C value? Much like when we were dealing with timber, when we're to the extreme right and we're talking about long columns, they tend to approximate Euler's buckling equation, and we call that elastic behavior. But when we're in the shorter range, of course we don't want to get our steel columns so short that we start to crush the material. But when we're on this side, we are dealing with the inelastic range. And so that C sub C value represents the theoretical line. Let's write this down. Represents the theoretical line between inelastic and elastic behavior. All right, now as you can guess, the behavior of the steel will be different whether it's elastic or inelastic, and because of that we have to have two different equations that account for the allowable stress. And so let's reference the allowable stress equations. One of the cool things about steel design, or steel column design rather, is that calculating these is simply a matter of looking at the slenderness ratio. And you'll recall that for steel, we don't do length over width, we do length over the radius of gyration. And we talked previously about what the radius of gyration is. It's a function of the moment of inertia It's again simplifying two parameters down into a single parameter that we can pull from the table. And also we have an adjustment factor K that accounts for the end restraints. We'll talk more about that just in a second, remind you what that is. But when you're looking at this slenderness ratio, if it's less than C sub C, in your textbook on page number 458, there's equation 2-1 that we would utilize. Now I'm going to write it here because it's quite a complicated equation, but you can see that in your textbook. If we're dealing with a KL over R ratio that's greater than C sub C, then there's a different equation. It's actually a little more simple than the first one. Elastic behavior is quite a bit more mathematically easy to approximate with an equation. And you'll see that in equation 2-2. Now these have funny equation numbers because they're referencing the Still manual that the industry utilizes. And so you can see those as I indicated on page 458. Now, for those of you who really love equations, go ahead and use those equations. For the rest of us, there's a cool approximation that makes this process way easier. And if you go into your textbook and look at tables 9.1 and 9.2, those show up on page numbers 461 and flip the page over, page 462. You'll see those two tables. Now, both tables work approximately the same. One of them, however, is for 36 KSI still. That's table 9.1. And let's label that 36 KSI still. And the other one is for 50 KSI still. Those are our two standard still strings. So you got to make sure you're on the right table. The only other thing to note is that if you're dealing with table 9.1, as we indicated up above, for 36 KSI still, the C sub C value is 126.1. That's that breaking point. Inside the table, any of these numbers of KL over R less than 126.1 utilize equation 2.1, and any of the values in the table that are greater than 126.1 utilize equation 2.2. So those equations are built right into the table, so there's actually nothing we have to do other than read the table to get our values. We're going to run an example here in a minute, and we'll show you how to utilize this table. But before we do that, I want to finish up our conversation for basic steel column properties and just have a quick reminder conversation about end restraints and the interaction equation. So let's begin with end restraints. Really quickly, the end restraints refer to whether the top and bottom of the column is pinned, fixed, or free, and one of those is the baseline value. Just as a reminder, when we assume that we have pinned ends, then that's the baseline value, and our adjustment factor K would be 1.0. When we're dealing with steel materials in general, we oftentimes assume that if it's a bolted connection, that it is a pinned connection, but if it's welded or has some web stiffeners or other means of making it a fixed connection, that we can go ahead and use a fixed connection. What I want to tell you is that pinned ends are often assumed simply because it's hard to determine fixity. It's hard to determine what those end values actually are and how close to being fixed they are. And so one of the common assumptions that we do that ends up being conservative is when they're doing design, they will often assume that pinned ends are utilized as opposed to a fixed connection. Now, another thing I want you to do is look at page number 459. There's a table, actually it says figure 916, but page 459, and it shows what the K values should be for a still column design. The bizarre thing about this table is it has theoretical K values which have been calculated. However, for the K values, there's a second row that you should utilize, and it's the recommended design value. What they've discovered is that when we're theoretically calculating these and compare that to the way they behave in the real world, it's not always exactly the same. And so they've adjusted those values just a little bit, and because of that you should use the recommended values. So for example, if you're looking at a fixed connection, that is the diagram A that is shown there, the theoretical K value is 0.5. That's the value that we showed up when we used timber. However, the recommended value is closer to 0.65. This accounts for that difficulty in determining the fixity and then the way it behaves in the real world. And as a quick reminder, K equals 1.0 for pinned. If we were going to be conservative and assume pinned, as we discussed just a moment ago, then K value would always be equal to 1.0. All right, one final thing that I want to talk about in this video is the interaction equation. As a quick reminder, the interaction equation considers both the compression load coming down the column, that is essentially the weight of the building. However, if there's any sort of lateral load acting on the structure, a wind load, something like that, or if we have an eccentric load that is offset causing some sort of bending within the column, then we would have to account for both the compression and the bending scenario that is caused. Page number 490 in your textbook has the interaction equation for still design. So page 490 has the interaction equation, and you'll notice that it's much like the timber equation. It's got quite a few parameters in there, but generally speaking, we're looking at the actual compressive stress divided by the allowable, and the actual bending stress divided by the allowable bending stress. This particular equation splits the bending stress into a strong axis and a weak axis and has you account for that. The only thing I want you to note is that this equation generally accounts for the P delta effect. That's essentially where we start to get enough bending that the compressive load that is there causes more bending, which causes more load, which causes more deflection, which causes more bending, and this is essentially what causes it to fail. So because we've already done the interaction equation for timber, I'm not going to actually have you do the interaction equation for steel, but do note that this is the proper way to do a still column design. We'll do the basic calculation for allowable stress and account for that, and make sure we know how to calculate the capacity coming down. This essentially becomes a piece that goes into the interaction equation, but for the sake of the steel portion of the course, from a conceptual standpoint, so long as you know that the interaction equation exists and should be utilized, we'll go ahead and lay off and just calculate what the allowable stresses are. And we'll go ahead and do that in an example in the next video.